Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is geotechnical soil structure interaction in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of our US office, and I'm also a sales engineer located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so within the GoToWebinar dialog box as shown here. We'll do our best to get to all the questions, but if by chance we don't, we'll certainly send you a follow-up email afterwards. So we'll quickly go over the content that I do want to cover over the next hour today. We'll give a brief introduction to the geotechnical analysis add-on for soil structure interaction available in the program RFEM 6. We'll talk about the different soil material definition types as well as the data input, and then we'll move on to our first example for today, shown over here on the right-hand side, for building soil structure interaction. We'll talk about how to input topics like boreholes and to generate our soil massif for our 3D soil solid. We'll go ahead and take a look at the analysis results and also talk about topics like settlements and the soil stresses. We'll then move on to our second example for pile design, which is also available with the geotechnical analysis add-on. We'll take a look at the pile input and of course run the analysis and how we can quickly generate a load displacement curve for the pile element. So here on the next slide, I want to just give a quick overview of the geotechnical analysis add-on and some of the benefits that it can bring to us. So with this add-on within the program RFEM 6, we can realistically analyze soil structure interaction. And we do so by directly inputting in what we call the soil boring logs. And we have the ability to generate the 3D soil solid, as we see over here on the right-hand side, shown below the structure. We also can consider the groundwater level within the soil solid, and we have several nonlinear soil material models available that we'll go through in more detail on the next slides. But ultimately, we're looking for a true integration of this structure for full soil structure interaction. So not only can we design this structure here, whether it's concrete, steel, or mass timber, but again, we can account for the behavior of the soil with this 3D solid. Then we'll take a look at information in the analysis results like settlements and soil stresses. So we might be wondering, why would we want to use this geotechnical analysis add-on as opposed to a more simplified approach where maybe we have a slab type element and typically we're used to in any FEA program just applying a spring support stiffness to the base of this element. Well, in comparison, the geotechnical analysis, as we just discussed, will generate this 3D soil solids instead, as we see over here on the right-hand side. Well, the first benefit is realistic soil structure interaction. So we want to capture the load distribution, the lateral pressures, and the shear interaction in all directions beyond what the simplified vertical support can provide. We also can account for the nonlinear and layered soil behavior. So we can account for the soil's stress-dependent stiffness, the plastic deformation, and the layered soil profiles for just better accuracy. We can also accurately predict topics like settlement and deformation. So with the soil solid, we can capture differential settlement, lateral spreading, and localized failure just much more effectively than this simplified approach. Carrying on to the next slide here, we have a few more points, including the advanced soil material models. So we have 4 material models available to us here that again we'll discuss in the next slide. So highly nonlinear material models available within this add-on. We can also couple the soil structure analysis. So not only can we analyze the foundation, but in the same file, we can analyze the soil behavior together, accounting for realistic load redistribution. So again, that true soil structure interaction. So all in all, we're going to have a better approach for complex geotechnical scenarios. So this is going to be ideal for deep foundations. We can even account for excavations or variable soil conditions where simply these surface springs fall short. So on this next slide, we do have a few modeling tips when we're talking about this 3D soil solid. The solid dimensions should be adequately defined when we compare this to the structure's dimensions. And this is an image taken directly from our online help manual here in the upper right-hand corner, where our structure is going to have the dimensions A and B. So therefore, these are the starting recommendations here for the size of our soil solid. But we highly encourage you to carry out what we call an edge distance results study. So ultimately, this may be the starting point, but perhaps we can decrease the size of this soil solid. That's going to generate a much quicker analysis, the smaller that this solid is within an FEA program, but we want to see less than 10% changes in the stresses at the boundary surface. If we continue shrinking the size of this solid model and we're seeing higher changes in stress at these boundary surfaces, then we know that our soil solid is not big enough. So we probably want to increase that size, again, to get accurate results here in comparison to the loads that we will apply to the structure as well as the size of the structure. We also want to ensure proper soil layer definitions. So with these complex nonlinear soil materials, the stiffness is going to increase with the depth. We want to ensure with topics like our borehole input that we are adequately inputting in the materials, the material properties, as well as the depths of these soil borings. And for the last point here, the program will automatically create the default boundary conditions of our solid element, but these are always editable. So as you can see here, again, another image from our online help manual, that with the soil solid, in the lateral directions, we are going to restrain the translation. At the bottom of the solid, we're going to set a support here so that translation in all three directions is fixed. And then of course, at the top here, number 2, the solid will be free to move. Now looking at the nonlinear solid soil material models available within this add-on. So soil is a highly nonlinear 3-part system, and this includes soil particles, water, and air. So therefore, we need to utilize special material models that mathematically represent this very complex soil behavior in something like an FEA program. So currently, when looking at RFEM, we have 4 material models available, including the modified Moore-Coulomb, the nonlinear elastic, and the modified hardening soil, as well as the Hoke-Brown. So now we will investigate each one of these material models. I think it's important to have a fundamental understanding of which each one of them can provide and maybe the best scenario to use this in your model. We'll begin here with the modified Moore-Coulomb. This is going to combine linear elastic and ideal plastic behavior. So essentially, we have a reversible linear elastic behavior within a stress limit zone. But when that stress reaches the yield point, then that's when the irreversible plastic behavior is going to begin. And this is all according to the Moore-Coulomb equations. The material will also fail when the shear stress exceeds the material's shear resistance. And these 3 points can be summed up here with the stress strain diagram for this material model type. So this modified Moore-Coulomb is really ideal for approximating the actual soil behavior, but with very few material property definitions. So the input here, once we get into RFEM, is quite a bit simpler than when we compare to the other material models. Our second material type is nonlinear elastic, and this is actually what we'll use in our first example today. So this is a hyperbolic nonlinear elastic behavior for this type of soil. It's a nonlinear stress strain curve with no plastic deformation. So this means that the deformations are reversible. This does have a stress that is dependent on the stiffness. So the higher the stress on the soil, then the higher the stiffness that it's going to provide. However, the stiffness is load path dependent, with the unloading and reloading stiffness is actually going to be higher than the initial loading. But it does not simulate plasticity or material failure. Again, just looking at the differences here with the stress strain diagram on the right-hand side. So this is really ideal to represent soil behavior under vertical loading with very minimal horizontal displacement. The third material type is a modified hardening soil. So this is an advanced elastoplastic soil model for nonlinear soil behavior. And for this one, we have elastic behavior soil stiffness that varies with the stress level for both the odometer and the triaxial stress strain responses. And again, we have two separate stress strain diagrams depending on the different conditions applied here. When the stress reaches the yield point, the elastoplastic with double hardening behavior will begin. The soil material is also stress dependent with the stiffness, in the sense that with the increased stiffness, we're going to have higher stresses. So when we look at much deeper soil levels, they're going to be able to resist deformations much better than we look at the soils maybe near the top elevation or top surface. So this can provide more realistic predictions compared to the simpler, more Coulomb model, and is really ideal for soft or over-consolidated soils. And finally, we have the Hoke Brown. This is going to combine linear elastic and ideal plastic behavior, but it's going to be specific to rock masses. So we have reversible linear elastic behavior within a stress limit zone. And this is all going to sound very familiar because the stress strain diagram, as you see, looks very similar to the more Coulomb. But when the stress reaches the yield point, we have irreversible plastic behavior, but this time it's going to be according to the Hoke-Brown equations. So this relates max and min principal stresses, capturing that nonlinear behavior of rock. So therefore, it's going to be ideal then to use this soil material type for modeling jointed rock masses where the strength decreases due to fractures. Okay, so we are finally ready to get into our first example today. When we do create a new model in RFEM, we are presented with our base data dialog box that we see here. And for those of you joining us today who are not familiar with the concept of our program, RFEM 6, RFEM is the base program. This allows us to fully model a structure. We have access to all the materials, the cross sections from all the various standards. We can load it and get a full static analysis. But under this second tab are all of the additional add-ons that we have available. So today, of course, we'll be focusing on our geotechnical analysis add-on that's activated here, but it's entirely possible if we wanted to also design this structure utilizing the design add-ons such as the concrete design. We could carry out the membrane surface reinforced concrete design according to the ACI or the CSA standard. So once we have defined this information, we are presented here in the main program. And I have already modeled this concrete structure, as you can see here, with surfaces and member elements, and the material is 4,000 PSI concrete. I also have applied a few loads directly to the structure. So using our dropdown up at the top to select here the dead load case, we'll go ahead and turn on the display of the loads. We have here just a general surface load at all three levels. When we look at the live load, same concept with a slightly different magnitude. And then we have a snow load. So all vertical gravity loads for today's soil structure interaction. Now, in addition to the material defined for this structure, I went ahead and also defined the materials here for our soil. So let us take a look at that in more detail within the material dialog box. Now, the first thing to know that when you do create a new material, we want to set the material type to soil. And this is only available because I have activated that geotechnical analysis add-on. Well, if we prefer, we could visit our library here and use our filters on the left to select the soil option. And we have a few soil input options that exist here that we could certainly use as a template. We'll continue adding more materials in the future as well. So we could bring those into this dialog box and again, use it as a template option if we'd like. Now, alternatively, we could just define all this information from scratch as well. But once we've defined the material type to soil, you'll notice here the material model. And here are those 4 different material models available that we went through within the PowerPoint slides. For today's example, I'm going to utilize the nonlinear elastic material. And I went ahead and put in the specific weight. Notice that you can specify here the drain specific weight versus saturated because we can input into the program where the groundwater table is located. Under the second tab is where we have additional information that is specific to our material. So perhaps we got this from the geotech engineer or we got this from the soil testing directly, but this is information that we are going to need input into the program. So I have 4 different soil materials here, including a filling, we have a sand, we have a till, as well as another sand material. Again, all nonlinear elastic, but the material properties are going to vary slightly. So once we have input in all of our materials, we're ready to create our first borehole. So I'll go ahead and collapse these folders over on the left here within our navigator. And you'll notice that we have the geotechnical analysis folder. And again, this is available because we've activated that add-on where we can right click here to create our first borehole definition. So within this dialog box, you can see here that we want to first specify where this borehole exists. So we can either graphically select it with this pointer option here, or we can input in the XYZ coordinates as we see back here in the model directly by typing them in. So that's what I'll go ahead and do today by typing in negative 91.67 in the X location. This will be 70.67 in the Y, and in the Z direction, this is going to be negative 0.5. So notice I am not placing this at the 0 elevation, which is where the foundation of my structure is located. I'm placing this 6 inches below the structure. And there's a reason for this that will come into play a little bit later on with what we call surface contacts, but just keep that in mind. Now we also can specify the groundwater location with the elevation input here of negative 11.5 feet in the Z direction or the vertical direction. And finally, we can populate down here our soil layers by using our drop down to simply select the materials that we have already defined within the model. So I'm selecting all 4 materials that I have input in. And the second column is where I will input in the depth that each material occurs within my soil testing. So the first depth is going to be 19.67 feet. I use my down arrow key. The next layer depth is going to be 3.25. Then we have 19.67, and the final depth is going to be 36.16. So we get a nice overview here of the elevation of each of the different soil materials. We can even see where the groundwater level is located as well. So once we have input in these different boring logs, and you'll notice here that I have already defined several other boreholes, I'll go ahead and turn these on graphically within the model. So under the second tab, under the geotechnical analysis, I currently have these turned off, so I'll go ahead and activate them. And we have a total of 5 boreholes defined here in and around the structure. So once these are now defined, we are ready to create what we call the soil massif. This will generate that 3D soil solid. So we can take a look at here, and I went ahead and already created this 3D soil solid, but let us go through it. So we can create a new definition type here in the lower left. And the first input is a soil massif type. We're going to set this to boreholes. I'll explain a little bit later on what the soil solids advantage is here, but for now with the boreholes, we can select this option and either graphically select boreholes number 1 through 5 or just type it in directly on our keyboard here. The soil massive center. So this should be placed as close to the center of the structure as possible. So we can graphically select this here within the model, or we could directly, again, type in the X and Y coordinate points. The soil massive dimensions. So we discussed this in the PowerPoint. These dimensions are really important. We want to make sure that it's adequately large enough that we're not seeing the stresses affected at the boundary edges, but we don't want to set it too large so that it affects our calculation time with no added benefit. So we have here the soil dimension in the A direction. So we have a nice picture here showing the A dimension. This aligns with the global x-axis. So we can see the x-axis here back in our model. I have set this to 200 feet. My B dimension is going to be set at 165 feet. This aligns with the global y-axis. We also can account for the groundwater within the soil solid by turning on this checkbox here. So when that is finished, I will go ahead and display here, because I currently have it hidden, is the 3D solid. So if I turn this into a solid rendered view, we get a nice look here at all of the different materials that were generated with the soil solid from the input of the boreholes. Now, notice that some of these boreholes exist outside of the solid, no problem. We're still considering that with the geometry here of these different solids, but we don't necessarily need to extend it clear out to these different locations. Okay, so turning this back into maybe a rendered view here with a transparency, you can see all of these green symbols. These are going to be our support conditions. And I also mentioned this in the PowerPoint that these support conditions are automatically generated for us. But we might be wondering, well, how can I make modifications to this soil solid? Because right now everything is dependent on these boreholes. Well, if we look at the basic objects here, we have the solids option, and the program has automatically generated 4 different solids for each material type. So you can see here solid 2, solid 3, and solid 4. Again, the geometry is dependent on the boreholes. What we have the ability to do is to go back to the soil massive here and say, okay, now that our solid elements are generated, I no longer want this to be dependent on the boreholes. Rather, I can toggle this to the soil solids. And now I have the ability, because it's referencing solids 1 through 4 here, to go back into the model to, excuse me, to make the modifications manually. Okay, we won't go ahead and do this. We'll leave this as dependent on the boreholes for now, but I think that's an important point to cover if we do want to make those manual changes. Okay, so now we need to discuss here the behavior of the foundation elements, such as these slab elements, to the 3D soil solid. And we do so with a nonlinear option in the program. And I'll go ahead and expand this here. Under these special objects, we have what we call a surface contact. So we'll right click to create a new surface contact. So this feature within the program allows us to define this geometric nonlinear behavior between 2 surfaces or groups of surfaces. So the first surface that we want to select here is going to be the top surface of my 3D solid that represents my soil. So surface number 1. The second surface, I want to define the behavior here with this slab on grade as a portion of my structure. The third input option here is a surface contact type. So with this option, we have the ability here to define the behavior of the contact perpendicular to the surfaces. And we've set this in the dropdown to fail under tension. So if we have tension between these 2 surfaces, we're not going to see any force transmission. But in compression, we'll see the 2 bearing on one another. Now, contact parallel to surfaces, so we're talking about the shear behavior. We have set this to fail if the contact perpendicular to the surfaces fails. And there's some different options you can select from here, but for example, today, this is adequate. So once we have input in this option, we click OK. That surface contact is defined. I also defined here a second surface contact. This is going to be for the grouped surfaces here for my isolated footings at the base of my column. You can see surfaces 18 through 21. And my surface number 1 here is again going to be that top surface of the soil solid with that same nonlinear behavior defined. So the reason why, again, I set the soil solid 6 inches below the foundation elements is because surface contacts cannot be in the same elevation. The program will give you an error. So I set the soil solid 6 inches below the foundation in the vertical direction because my foundation elements are 12 inches thick. So I considered half the thickness of these elements to again set that soil solid 6 inches below this elevation. Okay, the final thing to check here is the FE mesh settings before we move on to the loading. So under calculate mesh settings, and we talked a little bit about this in the PowerPoint here, but the target length for the finite element. So this 1.5 feet is going to refer to the structure element itself. And maybe we want to increase this here to something like 2 feet, just for a slightly quicker calculation. Should be worth noting too that you can always apply mesh refinements at specific surfaces or specific locations if you'd like. But notice that we have a 4th tab here for solids. So this solid element for soil has a completely different input for the FE mesh that typically is going to be much larger. Again, we want to take into consideration maybe something like an FE mesh study that we want to set the FE mesh large enough so that we're not really slowing down the calculation. But if we set it to something too large, then we're going to get inaccurate results. So we want to kind of find this happy medium here. So maybe for this example, I'm going to reduce the soil solid FE mesh to something like 6.5 feet. All right, so now moving on to the loading. We'll open our load cases and combinations dialog box. We already saw that we have applied the dead load, live load, and snow load to the structure. And now you'll notice that the program has automatically created this 4th load case for us for the self-weight of the soil solid. So this was automatically generated with the geotech analysis add-on activated. If we go back to this dead load up here, we are also considering self-weight, but this is for the structure, not the soil. So it's really important now that we address these static analysis settings when we are integrating this soil structure interaction. So let's take a look at these settings here. So by default, the program has the load cases set to a geometrically linear analysis. Perhaps maybe we want to increase the load increments to 4 here for a slightly more accurate calculation with these nonlinear materials. So this is perfectly fine for load cases 1 through 3, but we actually need to make a copy of this static analysis setting. We'll leave it at geometrically linear, the load increments to 4, but now we need to turn on this equilibrium for undeformed structure. This analysis setting is going to be specific for the self-weight of the soil load case number 4 here. So what exactly is this checkbox doing? Let us go back to the PowerPoint where I can explain this further. So this all refers to the initial state considerations of our soil. We want to account for the soil self-weight before the construction begins. So we're talking about adding in the structure self-weight. We're talking about before we add in the dead, live, and snow to the structure itself. So we want to calculate the soil self-weight in this initial load case. But here is the complex topic related to this, that this starting point, so I'm going to refer here to the stress strain diagram. This starting point is going to be this blue dot here. This is where we are now going to apply the additional loads to the structure, such as the dead, live, and snow. Well, we want to account for the soil's initial stress state and stiffness. So that's what we're doing here within this blue area, again, before we apply those additional loads. But we want to focus on the deformation resulting from the new loading. Again, this is the structure's dead, live, and snow loads, rather than the initial deformation from the soil self-weight. We want that deformation to start at 0, but while still considering the initial state of the soil for stress and stiffness. So that's why we enable this load cases equilibrium for undeformed structure within that analysis type. So we'll go back to the PowerPoint to ensure that this option is turned on here. We click OK, and then in our dropdown, we need to make sure that load case number 4 has this new static analysis setting activated here. Now, it really doesn't make a whole lot of sense to solve these other load cases here without considering the self-weight of the soil, so we can just go ahead and turn those off. But rather, we want to combine all these loads within the load combinations themselves. So we jump here to what we call the Design Situations tab. Now, design situations are automatically created by the program according to the ASCE 7 or the NBC standard. And all this is doing is creating this first design situation for our factored load combination. So grouping those load combinations together. The second design situation that is created here is our ASD load combination. So again, just kind of grouping together those unfactored load combinations from the ASCE. Now, for today, I'm not so interested in factored load combinations. We'll go ahead and turn those off, but we will go ahead and take a look at the unfactored load combinations. Now, before we jump to this load combinations tab, we do want to make some modifications here within the combination wizard itself. So we go into this definition here, and by default, everything's set according to a second order analysis. Well, I'm going to instead utilize this second default option, or I can make changes to the first input by utilizing that geometrically linear analysis. So this is the same static analysis settings that I just set for the load cases 1 through 3, nothing special there. But what we need to do is to turn on this initial state option, and we get a new tab here. So we want to consider the self-weight of the soil solid, again, as an initial state before we add in these other loads into the load combinations. Back to the PowerPoint, we're accounting for the soil self-weight that's going to modify the soil stress, the stiffness. That's our starting point. And then we add in these other loads from the structure. So once this is defined here, we need to make sure in our dropdown we select it, and then we can jump to the load combinations tab. So here are our unfactored load combinations listed, and you'll notice that each one of them has the initial state already activated because we made that change directly within the design situation. Now, I would suggest, because this calculation may take a little bit longer due to the solid, that we focus on maybe just a few controlling load combinations rather than solving for all of them. So for today, I'm going to focus on load combination number 4 here. So once we have defined all this information, we would run our calculation. And because this does take a few minutes, I am going to open up an already saved model. So here we are, exact same model. We have just run the calculation for load combination number 4, as well as that load case number 4. So we definitely had to solve for that as the initial state before we could solve for load combination number 4. And in our results, which you can see here are presented in our navigator with our 4th tab, we can immediately activate here the stresses within the soil solid. And we'll focus here specifically on sigma z. So this is going to be the normal stress in the vertical direction for our different soil layers here, again, within that 3D solid. But you'll notice that when I toggle back to the global deformation, this is 0. And that's entirely what we covered in the PowerPoint. Our starting deformation is going to be 0. But again, we are going to account for the stresses within the soil of this self-weight load case. So now moving on to probably the more interesting load combination number 4, where we have actually applied these loads to the structure. We can even turn them on graphically here to see them, the gravity loads applied. in addition to considering, of course, the soil solid. So beginning first here with the stresses within the solid, we have activated again sigma z, we've applied these additional loads. Well, we have a lot of useful features within the program that allow us to view these different results in different ways. So one of them that I would suggest is here under the type of display, we can toggle this to what we call the ISO bands for solids. And because we have set load case number 4 as an initial state for this load combination, we do have an additional option up here at the top that we can toggle between the final result, or we can view the differences to the initial state. So now we're not considering here the self-weight of the soil. Rather, we're only interested in what is the stress in the soil after we have added the dead plus live plus snow to this structure. So just kind of a useful 3D view here of exactly what's going on within the depths of that soil solid. We can toggle this back to the ISO bands here. Again, still viewing the stresses on the solid. If we go to a plan view, we can see exactly referencing our control panel over here, again, what those stresses are in that vertical direction. And finally, we want to take a look at here the deformations. So looking at the global deformations, what happens here is that we're also looking at the deformations of the structure due to the applied loads, but I'm really interested in first viewing the deformations in the soil solid. So we have the ability in this control panel to go ahead and turn off the display of all members. I'm also going to toggle here to turn off the display of all surfaces. And now we're only viewing the deformation within the soil solid itself. We can even increase the deformation factor here. We can go back to a plan view and zoom in and compare this to the global deformations given here in inches. What else will be extremely user-friendly when we're talking about these 3D solids is the use of what we call clipping planes. So we can go back to this first tab here within the navigator, and at the bottom, we have here what's called guide objects. And within here, we have the clipping planes. Now we have 3 clipping planes created by default, but of course you can always add in your own clipping planes or modify these, but we can right click to immediately turn on that clipping plane. That's just going to slice right through that solid. So now we can see the deformations as a function of depth here through the 3D element in RFEM. We can also take this clipping plane and slide it back and forth here. Another nice trick is that if we hold down the control key and we slide our clipping plane, it will actually move in 1-foot increments as well. So that's really addressing all of the result information for the 3D solid. But if we go ahead and turn back off this clipping plane and we go back to our results here, and I'm going to turn back on the results for my surfaces, I'll turn back on the results for my members as well. Remember, we're also interested in the additional stresses here or internal forces from the settlement of the soil structure interaction within the concrete structure itself. So what we can do here is to activate either the member internal forces or the surface internal forces. So for example, taking a look at here, the MX forces in our concrete surfaces or MY, and we can also toggle between here the final result, and I'll go ahead and turn this back so that we can see the values here of our bending forces within the surfaces, or the difference to initial states. We should see slightly higher internal forces, internal stresses, or whatever it may be with our results of our structure due to the settlement of this soil solid as well. And again, we can utilize those additional add-ons like concrete design to carry out the full structure design all within one file here according to the ACI or CSA standard. All right, we're now ready to move on to our second example. So for this, I'm actually going to go back to the PowerPoint here to talk about pile design. So this is something that's also available with the geotechnical analysis add-on, and there are a few requirements here if we do want to carry this out. The first is that we will release a new member type in RFEM called pile, and we'll certainly see this with our simple example today. Also, it should be known that we need to also activate here the construction stages analysis add-on for the calculation. And the reason why is that soil is a very stress dependent material property. It's very dependent on the load history. And we have these highly advanced nonlinear soil material models that can account for this behavior. But we require the CSA add-on to calculate the deformations and the stresses with simply higher accuracy when we're looking at something like the pile design. We also have only a couple material models that we can use here in that selected list of 4 that we have available. This would either need to be the modified Moore-Coulomb, which we'll use in our example today, or the modified hardening soil. The other 2 material types cannot be used with pile design. We also will integrate the pile, its line, so to speak, directly into these soil solids with an independent mesh. So why we do this is because the solid is the primary component and the pile is secondary. So we want this pile to kind of follow along with the behavior of the soil. And this will make more sense in our example today. The FE mesh length for the soil solid. So we talked about the FE mesh in example number 1. We want to set this to approximately the pile diameter. So that's just kind of the rule of thumb here with our 3D soil solid. The pile result element length, we want this to correspond to the size of the 3D soil element, which inevitably refers back to the pile diameter. This is also controlled in the mesh settings. We set this under the number of divisions for special members. Again, this will make more sense with our example once we get into it. Okay, so we will jump to our model here, and I already have generated in this model the 3D soil solid. The reason why is because we've already covered the basics in example number 1, so we don't need to go through these in detail again, but I will just give a quick overview here, and maybe we turn this to a solid rendered view. So for my materials, again, very simple example today. I've applied here 2 soil materials, maybe one for above the groundwater. This is going to be the modified Moore-Coulomb material type. Again, it can also be the modified hardening soil, but with pile elements, we cannot use these bottom 2. I've input in the relevant material properties as well as under the second tab. You remember from the PowerPoint way back when I talked about the Moore-Coulomb being a little bit simpler than the other input options with the material models. You can see why here. And then I have a second material just for below groundwater, maybe with modified soil property input. So once we've defined this, as we saw from example number 1, we would jump here to the borehole definitions. And you can see here that I have one very simple borehole for today defined directly at the origin. I did define my groundwater elevation at negative 11.5, and I have those 2 soil materials populated here in my table with the relevant depth. So again, nothing new here. If I turn this to a rendered view, we can see that borehole right there at the origin. So once we have the borehole defined, we can jump here to the soil massif. And I'm referencing borehole number 1. I place the soil center, the soil solid material just right here at the origin point. Now, this is a very simple example for today, a single pile element. So my dimensions here are set to something much smaller, 85 feet by 85 feet in both directions. And I'm also accounting for the groundwater. So again, we see that soil solid generated here. The next step is to draw our pile element. So the first thing I'll do is to go ahead and turn off the display of my boreholes graphically. And we create a new member element. And I am using my quick tools up here at the top to create a new single member perpendicular to the work plane. So when I select this, we would need to set here the member type. So as I mentioned in the PowerPoint, when we activate here the geotechnical analysis add-on, we have a new member type called pile. Well, under the second tab, this is where we specify the cross-section and material. So I have already defined here a 50-inch diameter, 4,000 PSI cross-section that I will apply to the pile, but keep in mind it doesn't necessarily have to be concrete. It could be a steel pile or any other shape that you see relevant. So once we have assigned this cross-section and material to this member, we now have this third tab here for pile. And this is where we input in the pile resistance type. So we create a new definition here. Now, this input is just going to refer to the resistance parameter. So up at the top for this pile element, we're going to input in the skin friction or the resistance along the pile shaft. And down here at the bottom is where we're going to input in the end bearing capacity, or what's the resistance at the pile tip. Now, this information is always dependent on the soils that we have. It's dependent on the geometry of the pile. My colleague gave a great webinar previously that you can refer to where she goes much more into detail on how to calculate this information. For today's example, we'll assume that we have calculated all of this outside the program, and we can directly input in here. The shear strength at the start and the end will be set to 1.25 kips per square foot. Okay, so moving on to the shear stiffness, we have here the input options that I will set to 3916 KSF at both the start and the end. And finally, we have the base resistance axial strength, which we're going to set as 22.35 KSF, and the axial stiffness is going to be set at 835.1 kips per foot. Okay, so now that this information is set, we click OK, and we're ready to draw this element graphically within the model. So I'll turn this to a wireframe view, and I'm going to set the member length here to 31 feet. Now notice if I try and snap here, the pile is in the wrong orientation. We can quickly use this button here to reverse that. And then I'm just going to input in here by selecting directly at the origin point my pile element. I'll go ahead and turn off a couple other things here. So you'll notice that this pile, if we turn this to a rendered view, is essentially drawn here directly within this soil solid. So I also covered in the PowerPoint the importance of integrating this pile in the solid. So we have to do this within the solid element itself. So we go back here to the basic objects. And again, because we've created that soil massif, the program generated two solids for us based on our materials. And within these two solids, we can simply double click to edit it. We need to add in this option, integrated objects. And we get a new tab here where I can tell the program to integrate this line as an independent mesh for my pile. And I can graphically select this line element in the model, line number 57, and I click OK. I'm going to do the exact same thing for the second soil solid. I'm going to integrate this here, and maybe this time I just directly type in line number 57 and I click OK. All right, so one more thing to do here before we move on to construction stages is to apply some type of load to the pile element. So going into our load cases and combinations, we have here both the self-weight load cases that are automatically generated by the program. So we have the self-weight of our structure or our pile element, and we also have the soil self-weight, just like what we saw in example number 1. Well, I'm going to create a third load case here that we will call live load, and we will modify the action category according to the ASCE 7 within this dropdown to live load. And I click OK. I go back to the model here where I'm going to apply a simple nodal load. So we're under the load case number 3 for live here. I apply a downward force of negative 375 kips. I can graphically select this point here at the origin. And once we click OK, we see this load applied here at the top of our pile. All right, so as I mentioned before, we do need to activate here the construction stages analysis add-on, and we do so by going back to our base data dialog box. The construction stages analysis can be activated here. And once we click OK, we're brought back into the program, and I'll go ahead and collapse most of these folders. We now have a new option to define the construction stages. So the CSA add-on is exactly as it sounds. We can create these different construction stages, maybe where we activate different elements in each stage, maybe we vary the loading in each stage, and that's going to be required for this pile analysis. So the first construction stage, I'm going to give it a comment down here that this will be the initial phase. And with this initial phase, we want to activate all surfaces and solids within the model. And this is really just specific to our soil. So we want to activate all solids, that's just solids 1 and 2, but we're also activating the surfaces because remember, these surfaces have these boundary conditions here, these restraints that we need to consider. So that's really all that's required within this initial phase. What we will do in just a minute in the static analysis settings is we want to convert this to a linear elastic material. But that will make more sense once we get to it. So we create our second construction stage here, and this one is going to be the kneel phase for our soil. We have no modifications here, no changes compared to the previous construction stage. We're still just looking at the soil solid, but once we get to our static analysis settings, we will convert this to a very highly nonlinear material model. The third and final construction stage, so we'll go ahead and create a new construction stage definition here, is where we want to activate both the pile and load phase. Now, as far as the construction stages, we're going to activate here at the member, and we go ahead and click all members. It's only member number 1. As far as the loading, we'll activate this when we get into the load cases and combinations. So here are our 3 construction stages. That's all that's required with this specific input, and we click OK. Well, we're going to go back into our load cases and combinations, and rather than in comparison to example number 1, looking at load cases and load combinations, I'm only going to focus here on the construction stages for my calculation, for my analysis results as well. So therefore, these 3 load cases, I don't need to solve for those. They still exist in the model. I just don't need to run a calculation for them. It doesn't make any sense to run those alone. Again, no load combinations defined here. We're purely looking at the construction stages. So here are the 3 that I listed. And now we need to assign here both the loading as well as the static analysis settings. So the first is that initial phase, and we go in here to take a look at the static analysis settings that I've already set. So geometrically linear, maybe we only have 1 load increment, that's fine. Nothing else really special about this particular static analysis. But what we do want to create is a structure modification. With this, we can create a new definition type here where we can deactivate the material nonlinearity, but only for this initial phase. So we're going to convert this soil material just to a simple linear elastic material type, and we click OK. So now this is selected here again only for construction stage number 1. Looking at construction, and actually one more thing to mention here is our loading. We want to consider here the soil self-weight only. Not necessarily the live load or the self-weight from the pile quite yet. We'll do that in the last construction stage. So looking at construction stage number 2, we want to take a look at the static analysis settings. I've already created this. This is a geometrically linear analysis, same number of load increments, but we're going to activate here that special setting we talked about, the equilibrium for undeformed structure. We're accounting for the stress and the stiffness of the soil, but not the deformation before we apply those additional loads to our pile element. So once we have defined this, we select it here in our dropdown. We are going to not activate that structure modification because we convert this back to a highly nonlinear material. Under the load cases, we're still just accounting for the soil self-weight, so nothing to do further here. And now we're finally ready to activate the pile member and the loading. So looking at these static analysis settings, I've created this third definition here geometrically linear, but notice that I've set this to 10 load increments. So we will slowly ramp up the loading up to 375 kips over 10 increments. And we have the ability to save the results of all of these load increments together. So once we have this set, we make sure it is selected here in our dropdown, and under the load cases is where we also want to consider the self weight of the pile and that live load as a permanent load. So we're finally ready to run our calculation for these three construction stages. We could click calculate all. And of course, for the sake of time, I will refer here to an already saved model with these results. So once the calculation is run, this is what we would be presented with. And we're probably most interested in this final construction stage. We've applied this 375 kips. We have our pile activated in here. And now under this fourth tab, we can view the global deformations. And perhaps we want to look at these in the vertical Z direction. Well, if you remember for this construction stage, we have 10 different load increments and we save the results for each one of these. So what's kind of great is that we can cycle through these different load increments as the load gets higher and higher so that we can see how the deformations are changing within the soil solid. We could also take a look at, the member internal forces as well, if we'd like, with those results. Okay, so with the results here, I'm going to go back to the model. And we want to check out the final stage here. Again, we're still in CS3. With the global deformations we already talked about, we can also activate here, just like what we saw with example number 1, the solid stresses as well through these different load increments, if we're interested in that. And then again, the member internal forces could be activated here with the internal forces as we move through those different load increments. So a lot of similarities. We could use clipping planes and everything else that we saw in example number 1. The final thing that I would like to just quickly show you here is how to create what we call a load displacement curve. So under the project navigator here in our first tab, we have what we call these calculation diagrams. And we can create as many calculation diagrams as we want. The big benefit of this is that we don't necessarily have to export our result information to something like Microsoft Excel and create these diagrams and graphs manually, but the program has this implemented in here. So we could select here from our dropdown for our new diagram a chained analysis option. The final construction stage to consider is CS3. So that's going to be once we've activated both the pile and the loading. And then the start construction stage would be CS2. Well, within the horizontal axis drop-down options, you can see all the different options that we have available to display here, but perhaps we choose something like maximum deformation in the global Z direction. In the vertical axis, we can choose something like the member internal forces, and we're probably most interested in the axial forces of this pile. We select here graphically member number 1, and then we could choose here the node that we're interested in, which I would probably choose this top node here where that load is applied. And this diagram is automatically generated for us. We could add it to our printout report. Again, we could create multiple diagrams here, and this would probably look a little bit more interesting with a more complex model. Maybe we have more construction stages where we have different loading varying through the stages themselves, but this is just a quick example to quickly show this to you. Now, also keep in mind that, of course, this was a very simple example for pile design, but we could refer back to example number 1, put piles underneath this much more complex structure, this concrete building, and integrate it with the soil solid as well, with surfaces and other elements. So again, we aren't just restricted here to this single pile element, of course. Okay, so we will go back to the PowerPoint to conclude our webinar today. I did just briefly want to talk about a couple of future developments that we're working on. So we certainly have a long list of development features that we're working on with the geotechnical analysis add-on, but I wanted just to list a couple that are currently in work and should be available within the near future. The first is additional soil material models. So we are also working on the CAM clay model. So this will be a soil material type used to represent clay soils, including this clay soil behavior under the different loading conditions. We're also working on the jointed rock model. So this will be used to represent rock materials with jointed or fractured characteristics. So you can keep an eye out for that in a future release with this add-on. The other really cool thing that we're working on is the 2D constrain modulus method. So what we want to do here is to automatically determine the surface support condition. So we're talking about the elastic spring coefficients directly from the soil properties that you input into the program. So what I mean by this is we'll calculate this according to a nonlinear iterative method. And remember, I talked about the PowerPoint way back when of this simplified approach versus the 3D solid. Well, this refers to the simplified approach with just placing spring elements underneath the surfaces, for example, but we're going to calculate these spring coefficients or these spring values automatically for you directly from the different soil properties. So this is certainly a more simplified method compared to what we saw today with that 3D soil solid, but could be a big advantage in some scenarios for your models if you wanted to take that more simplified approach. Okay, so if you liked what you saw today, you're interested to learn more about RFEM, the Geotechnical Analysis add-on, or any of the other products that we offer, it'd be great if you reached out to our sales team. We'd love to set up an online demo, an online meeting with you. You can utilize the QR code here. This is also available in the PowerPoint that I've attached to the GoToWebinar, or just directly access our website at deluwell.com, and you can see our contact information down here at the bottom of our screen for our Philadelphia office. We will have many more upcoming webinars. I hold these approximately once a month. You can register at deluwell.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so keep an eye out for that for these future webinars. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So this is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. And if you watch with a colleague or you watch in a conference type setting and you yourself did not register for this GoToWebinar and you are wanting PDH, you'll need to request that at the email address shown here, info-us@deluwell.com. Just let us know who you watched it with and we can certainly issue that PDH. So again, if you yourself did not register and you're wanting the PDH, go ahead and send us that email here. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next one. Thanks so much.